You owe your friend $100 for dinner, so you pull up your banking app, tap their name, and press send. But at the exact moment the money request hits the bank server, your phone battery dies. The screen goes black. This creates a problem. If the power dies after the money leaves your account, but before it reaches your friend, where does that $100 actually go? We usually expect the digital world to be instant and perfect. In reality, servers crash and power grids fail every single day. Your money stays safe because databases use a safety net called log-based recovery. It is a set of rules that ensures your data survives even if the computer's physical hardware fails. To see how this works, let's step inside the bank's database. Think of the system as an extremely cautious bookkeeper. This bookkeeper keeps a permanent, secure record called the log. The database uses this file to record every action it intends to take before it actually takes it. The system follows a requirement called write-ahead logging. This rule says the database cannot change any real account balances until it writes its full plan into the log first. The log records the transfer in sequence. First, start transfer. Second, take $100 from account A. Third, give $100 to account B. Once these steps are committed to the log, the database finally moves the actual money. Write-ahead logging acts as an insurance policy. Even if a crash happens a millisecond later, the system has a permanent step-by-step record of exactly what it was doing. Let's revisit that crash. This time, we'll look at the database as it wakes back up after the power returns. The database reboots with no memory of what it was doing. Its first task is to check its permanent log to see if any work was interrupted. The system sees the entries for start and take from account A, but then the record simply stops. There is no entry saying the job was finished. Because the finished entry is missing, the database knows it has an incomplete task on its hands. It can't leave the money in limbo. The system fixes this by reading the log backwards and reversing every step it took. It adds the $100 back into account A, effectively erasing the mistake. This process enforces the all-or-nothing rule. A transaction must either finish completely or not happen at all. This ensures a computer glitch can never leave you with a half-processed payment. Now imagine the opposite happens. The transfer finished, but the server crashed before the final results were saved to the main hard drive. When the system reboots, it sees the finished stamp in the log. It simply repeats the recorded steps to ensure the $100 is securely placed in account B. As a database runs for months or years, the log grows massive. Reading the entire history after every crash would take far too long. To stay efficient, the system uses checkpoints. These are periodic markers that act as bookmarks in the log. A checkpoint tells the system that everything before this mark is already safely saved. After a crash, the database only has to read the few entries that happened after the last bookmark. By combining these bookmarks with the redo process, databases ensure that completed work is never lost while keeping recovery times very short. This planning and recovery process repeats across the millions of servers that keep our world connected on a global scale. When a hospital updates a patient's medication list, or an air traffic controller assigns a flight path, the systems use this same plan-first method. It ensures that even in a total blackout, a patient's prescription or a plane's location isn't left in an uncertain, half-finished state. The log serves as a survival guide for the database, providing a clear path back to a consistent state after a failure. So the very next time your phone dies mid-purchase, you don't need to worry about your money vanishing. You can trust the system to handle the recovery. Deep in the code, the log has already recorded exactly how to fix the interruption.